Welcome back to Dr. Liu's VCE Chemistry channel. Today, we are breaking equilibrium and rate of reaction from the 2025 VCE Chemistry exam. In this video, we use first principles and physics logic to deconstruct the most intimidating part of VCE Chemistry Unit 3, equilibrium and reaction rates. What you will learn: the essence of stoichiometry, why it's essentially applied physics conservation of mass, the ICE Table Syllogism, how to build a logical map so you never lose track of a mole again, linguistic precision, why defining reversibility correctly is the gatekeeper to your 40+ study score, the QC versus KC decision chain, a 3-step quantitative framework to secure every calculation mark. Here is a breakdown of why this is the case based on collision theory and the role of a catalyst. Why option C is correct. A catalyst works by providing an alternative reaction pathway with a lower activation energy, EA. By lowering the energy barrier required for a successful collision, a greater proportion of particles now possess kinetic energy equal to or greater than the new, lower activation energy. This leads to a higher frequency of successful collisions and thus increases the reaction rate. Why the other options are incorrect. A and D, both the speed of particles and the overall kinetic energy of the system, are determined by the temperature. A catalyst does not change the thermal energy or the velocity of the individual molecules. B, while the frequency of successful collisions increases, the total number of collisions per unit time remains essentially the same. To increase the total number of collisions, you would typically need to increase the concentration, pressure, or temperature. We are given an initial chemical system, labeled initial reaction equilibrium, that combines nitrogen and hydrogen gases to produce ammonia, with a known Kc value of at 500 degrees Celsius. The core challenge is to determine the equilibrium constant for a second, target reaction. Step 1. Reaction reversal. We begin by modifying the initial reaction equation. As shown in the box labeled reverse reaction, the entire system is flipped. Products, ammonia, now become reactants, and reactants become products. Crucially, the fundamental rules of equilibrium state that when you reverse a reaction, you must take the reciprocal of its equilibrium constant. We take the original Kc and divide 1 by it. This action is mathematically represented by the green call-out box, reciprocal of Kc. Step 2. Coefficient scaling. After reversing the reaction, we apply a second transformation. In the box labeled Multiply Coefficients by2, we see that all molar coefficients have been multiplied by a factor of 2. For instance, the original 2 moles of NH3 become 4 moles, and the single mole of N2 becomes 2 moles. This multiplier is represented by the exponent icon, squared. The second green call-out box highlights the rule. When you multiply coefficients by a factor, the equilibrium constant is raised to the power of that factor. In this specific case, the Kc from the previous step is now squared. (1) Analyze the reaction. The equation provided is exothermic forward reaction. Since delta H is negative, the forward reaction releases heat. Endothermic reverse reaction, the reverse reaction absorbs heat. 2. Predict the shift. At T equals 10 minutes, the temperature is increased. According to Le Chatelier's principle, the system will act to oppose this change by absorbing the extra heat. The system shifts in the endothermic direction, to the left. Result: the concentration of the product NO2 will decrease, and the concentrations of the reactants NO and O2 will increase. 3. Identify the graph characteristics. Temperature changes have unique signatures on concentration time graphs. Gradual change, unlike a change in concentration, which shows a vertical spike, or a change in volume or pressure, where all concentrations spike, a temperature change causes a gradual curve for all species starting exactly at T equals 10. Direction of curves. NO2 should curve downwards. NO and O2 should curve upwards. 4. Evaluate the options. A. Shows a spike in NO2, which implies a concentration addition, not a temperature change. Incorrect. B. Shows NO2 increasing. This would only happen if the temperature were decreased. Incorrect. C. Shows a gradual decrease in NO2 and a gradual increase in both NO and O2. This perfectly matches our prediction for an exothermic reaction being heated. Correct. D. Shows spikes in the reactants, implying they were physically added to the container. Incorrect. A reversible reaction is a chemical process in which the conversion of reactants to products and the conversion of products back to reactants can occur simultaneously. Alternative, shorter version. It is a reaction that has the ability to proceed in both the forward and reverse directions under the same conditions. 2. Explaining the pitfall, the equilibrium trap. In English, we can explain the common student error using the distinction between capability and status. The logical error. The most frequent pitfall is defining a property, reversibility, by describing a specific state, equilibrium. Reversibility is it describes what the reaction is capable of doing, going both ways. Equilibrium is it describes what is currently happening at a specific point in time, rates are equal. Why the rate explanation fails. If a student writes, it is a reaction, where the rate of the forward reaction equals the rate of the reverse reaction, they have described dynamic equilibrium, not the reaction itself. A reversible reaction is still reversible the very microsecond you mix the reactants, even though, at that moment, the reverse rate is 0 because no products have formed yet. Therefore, the equal rates definition is too narrow and logically incorrect for a general definition. 3. Linguistic note, proceed versus proceed. This is a common phonetic pitfall for students during exams or oral presentations. Proceed, to go forward or continue. Second syllable stress. The reaction can proceed in either direction. Proceed, to come before something else in time or order. Second syllable stress. Reactants precede products in a chemical equation. The yield of methanol will decrease. Since the forward reaction is exothermic, delta H less than 0, an increase in temperature causes the equilibrium to shift to the left, the endothermic direction, to absorb the added heat, resulting in a lower concentration of products. Marking criteria, 2 marks. Mark 1, identifying the decrease in yield. Mark 2, explaining the shift in the endothermic direction, to the left, to oppose the temperature increase. Pitfall alert, students often confuse rate and yield. While a higher temperature makes the reaction faster, it makes the result, yield, worse for exothermic reactions. To increase the yield at a constant temperature, you must change the pressure or concentration. Option 1, increase the pressure, or decrease volume. Justification, there are 3 moles of gas on the reactant side, CO plus 2H2, and only 1 mole of gas on the product side, CH3OH. Increasing the pressure causes the system to shift toward the side with fewer gas molecules, the right, to oppose the change, thus increasing the yield. Option 2, increase concentration of reactants, or remove product. Justification, adding more CO or H2 creates a stress on the system. To oppose this, the system shifts to the right to consume the added reactants, increasing the yield of CH3OH. Marking criteria. Mark 1, state correctly identify one valid change that increases yield at constant temperature. Example, increase the pressure of the system or add more CO or H gas. Mark 2, justify explain the shift using Le Chatelier's principle and the specific reaction stoichiometry. The system shifts to the side with fewer gas molecules, the product side, to oppose the increase in pressure. Key pitfalls to avoid in the justification. Missing the oppose logic. VCEA markers look for the phrase to oppose the change, or partially counteract the change. Simply saying it shifts right, without explaining why the system does so usually results in losing the second mark. Stoichiometry specifics. If you choose pressure, you must mention the number of moles. Correct, 3 moles of gas on the left versus 1 mole on the right. Incorrect, the right side has less gas. Too vague. The rate trap, never mention that the reaction becomes faster in this specific answer. The question asks for yield, so your explanation must focus on the position of equilibrium, not the speed of the molecules. When you approach a question on Le Chatelier's principle, remember that VCEA markers are looking for a very specific logical chain, and falling into a few common pitfalls can cost you easy marks. First, never describe the nature of a reversible reaction by its state at equilibrium. A common logic gap occurs when students define a reaction using equal rates. Remember, reversibility is about the capability to proceed in either direction, regardless of whether equilibrium has been reached. Secondly, avoid vagueness in your justification. You must provide explicit stoichiometric evidence by comparing the gas moles on both sides. Simply saying one side has more gas is insufficient. You need to quantify it, for example, by stating 3 moles vs 1 mole. Furthermore, ensure your answer includes the counteraction clause. You must explicitly state that the system shifts to oppose or partially counteract the change you've applied. Without this, your logic is incomplete. Finally, do not let rate-yield confusion trip you up. Even if a temperature increase makes a reaction faster, for an exothermic process, it will always drive the equilibrium to the left, decreasing the yield. Keep your discussion of how fast separate from how much, and you'll secure those 2 marks. According to Le Chatelier's principle, if the pressure is increased, the system will shift to oppose the change by favoring the direction that produces fewer gas molecules. Since there are 3 moles of gas on the reactant side and only 1 mole on the product side, the equilibrium will shift to the right, thereby increasing the yield of methanol. A major pitfall in this 3-mark question is providing a qualitative guess without the supporting math. VCEA markers strictly require the calculated value of QC to award the first mark. Another common logic gap is failing to state the why behind the shift. Don't just say it shifts left, you must explicitly cite the comparison. Because QC is currently too high, QC, KC, the system must reduce the numerator, products, and increase the denominator, reactants, to restore balance. Finally, watch the units. While Kc is given as molar to the power of -2 here, ensure students don't get confused by the power of 2 in the denominator during the calculator entry. A simple calculation error here will cascade through the rest of the logic. When tackling a 4-mark equilibrium calculation like this, the ICE table is your best friend for maintaining logical clarity. The first critical step is to identify the change row. A common pitfall here is ignoring the stoichiometric coefficients. Since the ratio of H2 to CH3OH is 2:1, producing 1.30 moles of methanol requires the consumption of exactly 2.60 moles of hydrogen. Failing to double this value is a frequent logic gap that will derail your entire calculation. Next, you must transition from moles to the equilibrium expression. Because the volume is 1.00 L, the molar amounts and concentrations are numerically identical, which simplifies our KC setup. However, always be wary of the algebraic trap. When you substitute these values into the 1.21 equilibrium constant expression, don't rush to expand the quadratic. Instead, to solve for x, we have x minus 2.60, all squared, equals 0.29. Instead of expanding the quadratic, we take the square root of both sides to isolate the term inside the brackets. Finally, ensure your final result reflects the precision of the provided data. Since our inputs are given to 3 significant figures, your answer for the initial amount of H2 must be rounded correctly to 3.14 moles. Precision in your final step is what secures that 4th and final mark. This 4-mark calculation is where the stoichiometric ratio becomes a high-stakes factor. The most frequent pitfall is the coefficient oversight. Students often forget that for every 1.30 moles of methanol produced, 2 moles of hydrogen are consumed. Missing that 2 times 1.30 in the change row is a guaranteed way to lose at least 2 marks. Another logic gap occurs during the algebraic phase. Some students struggle with the square root in the KC expression, often trying to expand the quadratic unnecessarily. I always advise my students to isolate the squared term first, it's much cleaner. Finally, watch the significant figures. Since the inputs 5.00, 1.30, 1.21 are all given to 3 SIG figs, the final answer must be 3.14 moles. An answer like 3.1 or 3.1388 might result in a 1-mark deduction in a strict VCAA assessment. Core concept, the collision framework. Catalysts, Q14 lower EA increase proportion of successful collisions. Note, EC is temp dependent only. Equilibrium, KC, logic, Q15 mathematical rigor in reversing scaling reaction expressions. Graphing change, Q16 temp shifts show gradual curvature, concentration spikes indicate addition or removal. 2. Extended response, the logic chain. Defining reversibility, 3A focus on the capability of the system, not the current equilibrium state. Rate versus yield, 3B.I separate kinetics, temp up equals rate up, from thermodynamics, exothermic plus temp up equals yield down. Stoichiometric justification, 3B.2 use explicit mole counts, 3 moles vs 1 mole gas, to justify pressure shifts. 3. Quantitative rigor, the ICE method, 3CD. The QC decision, calculate, then compare, and final conclude. QC larger than KC induces shift left. ICE table discipline, enforce the stoichiometric ratio. Algebraic precision, isolate terms before square rooting, final answers must respect significant figures. 4. Examiner's checklist, VCAA pitfalls. Oppose the change, the mandatory clause for all the Chatelier justifications. Precision over vagueness, replace less gas with specific stoichiometric evidence. Notation, use equilibrium arrows, D, to define the nature of the reaction. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.